and decided that they would come up with some new terms, kind of like they came up with the word switch instead of a multi-port bridge. So, but the idea here is that you can build a network that's has fault tolerance, and it can be added onto very easily. So let's talk about 3-tier and two-tier networks. This is classic Cisco stuff. Now this is solid here. The classic Cisco networking design philosophy is a 3-tier structure. That means that access layer, distribution layer, and core layer. So in a large complicated network, you might use all 3 layers. Like at Tarrant County College, we use all 3 layers. A smaller company might use only a 2-tier layer where they sort of collapse the core and the distribution layer all into one particular layer of switches. But the idea is we're going to use very inexpensive access layer switches to connect to all our end points, our end devices like desktop PCs and telephones and printers and servers and things of that nature. And then we're going to use the more expensive distribution and core layer switches to aggregate this traffic and connect it back and forth to each other. Now let's see, do you guys remember from the STP chapter that the STP was optimized for a 5 to 7 hop link between any 2 access layer devices? So in theory, any packet you send out from your desktop PC would go through your access layer switch, go up through his distribution layer switch, go to his core switch, maybe to a second core switch, then down to a distribution layer, then down to an access layer, and to that end station you were talking to, instead of going through a hodgepodge of a bunch of switches that have been daisy chained together. So let's look at this access layer thing. Access layer switches, very cheap, inexpensive switches, like our Cisco 2960 switches, they're like $500 a piece. Well, they only have 24 ports. They don't have power over Ethernet. They don't have the 48 ports that you can stack in that blank sheet metal on the left part of it. They're not gigabit Ethernet speeds. So actual machine you would probably use in a production environment, you would want 48 ports. You would probably want a gigabit Ethernet to your client machines and maybe 10 gigabit uplink ports to the other switches. You would want power over Ethernet because you have Cisco phones that you have to operate with. Stand by. Just collecting attendance. So those switches are more like $2,000 a piece. The ones that we actually have in our wiring closet that I can't let you guys in and look at it. I can't even get in there and look at it because I don't want anybody messing with it, especially smart like Cisco people. So these access layer switches are the place where you plug in an endpoint device like a desktop employee PC or a Cisco telephone. In our case, our desktop PCs plug into a Cisco telephone, and then the Cisco telephone plugs into the wall jack that goes back to the wiring closet. It plugs into that port. And there, in turn, those uplink ports on those fairly inexpensive access layer switches are usually 10 times what the client machines connect to. So in the Cisco lab, we have 24 fast Ethernet ports and 2 gigabit ports. And we can plug in either copper or we can plug in a transceiver and do fiber optic cable. In the ports, in the switches that we use in our actual wiring closets, it has 48 gigabit Ethernet ports, and then it has 10 gig ports that use fiber optic cable to go back and forth to the other buildings, so we don't have to worry about that 328-foot distance limitation that we have with twisted pair copper cable. So at the access layer, what kind of security are we going to do at the access layer? Well, you remember when we did port security? We told the switch port to memorize the dean's MAC address, and if somebody snuck into the wiring closet and unplugged the dean's computer, and he would never notice because he's always off at meetings, and he'd plug in his own device because he's trying to break into our network, well, he would not have the dean's MAC address, and the port would go into the air disabled state and would block all the traffic from that unauthorized device. And then we could either do air disable recovery, and we recover after we unplugged it, or some system administrator network technician might have to do a shutdown and no shutdown on that port to turn it back on again so the dean could start using his computer again when he came back from all his meetings. So we would do layer 2 data link layer security on an access layer switch. Distribution layer switches are the next layer up. We're going to run fiber optic cables from all of those access layer switches in the wire closets. And we're going to run those to, in the case of the South Campus, it runs to the building next door, the academic classroom building, that block of 4 buildings around a big patio, and connects to a distribution layer Cisco switch that's in there. I think we're still using the old Cisco 6500 switches. We got some bond money from the taxpayers though, so they're probably going to replace those with the 8 and 9000 series switches pretty soon now. So at the distribution layer, we're going to aggregate all this traffic from all the access layer switches. And if we're going to do any type of access control list, security filtering of packets, we're going to do this at the distribution layer. If we're going to have any quality of service code, like for our voice over IP telephone service, we're going to do this at the distribution layer. And while it was more common previously to do data link layer Ethernet connections between the distribution layer and the core layer, these days it's considered better practice. Well, we have to run data link layer Ethernet switching with spanning tree protocol down to the access layer, because people might plug in some switch they bought at Office Depot between two cubes and create a loop and create a broadcast storm. So we have to enforce STP at the access layer switches. And the access layer switches would uplink to the distribution layer switches. But once we get to the distribution layer and go to the very fast core layer, you could go ahead and still use spanning tree protocol and just use standard Ethernet. But a better trend would be to use layer 3 switching, like OSPF. And that way you don't have to have spanning tree protocol on. You can do load balancing across all your links between the distribution layer and the core layer. So in order of expense, the access layer switches are the cheapest. The distribution layer switches are the more expensive switches. Kind of like that 4000 series switch we had in the back of the classroom. That's about a $20,000 switch. And it's a fairly small one. They can get higher than that. The core layer switches are the backbone of the network. They connect everything together. And they're going to give us our high-speed connectivity. And we don't want any access control lists or security code on those core layer switches, because access control lists slow a device down. He's got to look at every packet, and it breaks the Cisco express forwarding and fast switching capabilities that the engineers have put into that device. So if we look at a 3-tier network, oh, this is a terrible diagram. I'm going to use a better diagram than this one. Okay, so a 3-tier network, you have a core switch, then you have distribution switches, and then you have the access layer switches that actually connect to it. In a smaller device, a smaller network, we might only use a combination of distribution and core layer, collapsed core design, and if you're a smaller company, you wouldn't buy that many switches. Let me go ahead and switch to this other diagram here, which I think is a better diagram. Let me see if I can unshare this. Okay, here's a King Kong network design. I like this diagram because most diagrams don't show, they show the bottom 3 layers. They show access switches at the bottom, they show distribution switches in the middle, they show the core, and they don't show those upper layers up there, and they don't give a good impression here. Let's look at a particular, this is a good example of maybe the Tarrant County College or a corporate network. We have, at the upper part, we have access layer switches that go to all our employee PCs and telephones and so forth. Those connect to their own distribution layer switches, and all those distribution layer switches connect to the common core switches in the middle of the diagram. Then at the bottom on the left-hand corner, we have our WAN connections, our private leased WAN circuits that go between the campuses. They connect to their access layer devices and their distribution devices and connect to the high-speed core. We have a data center at Trinity River downtown. Many companies have their own built-in data centers. So the data centers would have switches that are optimized for servers at data centers, probably 10 megabit or 25 M, higher speeds than you would go to desktop machines. And those connect to the distribution layer switches of their own, and then they would connect to the common core switches. And then our internet connectivity for our whole company, they would have their own routers that connect to the internet and go through firewalls and then connect to distribution layer switches and connect to the core of the campus. So let me see if I can, will allow me to scroll this. Is this going to work? Oh, good, this is going to work. So this is bad design. This is not, they have all these hodgepodge connections between the data center and a switch that goes to employee PCs. And they have this hodgepodge connection between the dial-in telephone network and the ISDN lines and the WAN and the internet connections. This is not good design. The good design is dedicated core switches and dedicated distribution switches for each of the buildings that have employee PCs to be connected, dedicated distribution switches for our private WAN links to the other campuses, dedicated distribution switches for the data center, and dedicated distribution switches for our internet connectivity for all our employees. So this is on that, it's on my PowerPoint slideshow, my course presentation materials. It says something about slide 14, and it's just below the chapter 11 stuff that we're covering today. Okay, but oh, come on, can I? Oh, you're gonna make me go through all these slides again? Come on now. Okay, so switch networks. The older trend was to be Ethernet switching. Of course, from the access layer, we have to have switched Ethernet connections with spanning tree protocol to all our endpoints, like our telephones and our printers and our employee PCs. Then we would have switched connections between the access layer switch and the distribution layer switch. Spanning tree protocol, redundant connections. Anytime we have redundant connections, spanning tree protocol is going to shut down some of those links. But we have to have this triangle configuration, which is the most, use a triangle configuration. You see the little triangles between the access and distribution layer. Triangles are better practice than using squares. And then we would have switch connections, again, running spanning tree protocol between the distribution layer switches and the core layer switches. So at least you should get rid of the spanning tree protocol between the core layer and distribution layer and make those layer 3 OSPF or some type of scalable, good, high quality network layer routing protocol. Even today, the trend in the most modern networks is they are getting rid of the spanning tree protocol between the distribution layer and the access layer switches. And the only spanning tree protocol required is in the access layer switches that go to the endpoints to protect us against people in the cubes that would plug two ports together or try to put a hub or a switch they got from Fry's Electronics and plug two devices together and create a broadcast storm. Cisco even has a newer technology called overlay technology, and there's more information about that. That slide 14 that I showed you, that's the really CCNP level stuff, but it's got some great examples of network design, something that Cisco calls as an overlay design, where no spanning tree anywhere. It's going to be layer 3 all the way to the desktop. Each desktop will establish an OSPF adjacency with this access layer switch. And that's a technique that Cisco is experimenting now and pushing out to their customers. Okay, let's look at some techniques now for redundancy, multiple links, scalable routing protocol, and wireless connectivity. So first of all, he's talking about we want to plan for redundancy. So don't just run one switch and then go to another switch. Instead, we're going to run redundant multiple connections so that if one of these fiber optic cables gets dug up when they're tearing down the rotunda. I hope they don't dig up any fiber optic cables because I know there's stuff down in the basement in there. I used to run down there all the time before when we would run cables between the mainframe connections. So they're going to have to be careful when they tear that building down not to dig up any fiber optic cables. But if they do happen to dig up one, well, we have alternate connections, one that would loop around it and go to the academic classroom building, or one that would loop around the old rotunda and go to the library, so that if some connection gets dug up, we have protection against, we have redundancy, so we have fault tolerance, so we can keep doing our operations. So this means duplicate switches. It's an additional expense. And if something fails, think about a RAID drive array. In a RAID drive array and a server, any one hard drive can fail and you don't lose any data. Your disk channel might slightly slow down a little bit because he's having to pick up the redundant data off the remaining drives that are good, but you won't lose any data and your employees will still be able to punch in data and do their work. The problem with layer 2 Ethernet networks at the data link layer is if I make a loop, that would cause a broadcast storm. Because when we looked at the STP, if you create an Ethernet broadcast frame like an ARP request and there's a loop, well, the default topology of the switch is to flood the broadcast out all the ports. including the ones you set up as a loop, so in case one gets dug up, another exists. So spanning tree protocol, we have to turn that on, and that's on by default in Cisco switches to protect against that. However, we've lost the capability of the extra bandwidth, so we're going to use something like Ether channel to increase the bandwidth here. That's coming right up in a new slide. So what we want to do is reduce the situations where fault tolerance is if any one single device fails, if any one single wire is dug up, everything continues operating normally. Maybe we have slightly reduced bandwidth. If the disk drive fails on the server, we have slightly reduced disk channel speeds, but we still can do stuff. So we want to make sure that these failure domains are such that if any one single thing fails, the network won't go down. We'll be able to continue to do stuff. So normally we try to run extra lines instead of running 2 fiber optic cables from our building to the library and 2 fiber optic cables from our building to the academic classroom building. Instead of running 1, run 2. Of course, STP is going to shut 1 down. So we're going to configure them as port channels and make them Ether channel so that they're logically treated as one doubly fast line between our building and the adjacent building that we connect to. And that way someone can dig up fiber optic lines when they're tearing down the building, and we'll still have some alternate connection that could work. So Ether channel sort of load balances between links. It's not as good as OSPF, but it can be configured to sort of load balance. And if you got hundreds of clients anyway, it doesn't make much difference. So it'll balance. If I have 2 10 gigabit links to go to the library, I've really got 20 gigabits now. And STP hasn't shut off one of them, only give me the 10 gig. Now, a lot of times most companies have put in wireless access points. So we have, for example, in the center of the classroom, we've got a Cisco wireless access point that's stuck to the ceiling, and it is hardwired with a twisted pair Ethernet cable, copper cable, back to the wiring closet that's just outside the classroom door. And so that wire does 2 things. It gives the Ethernet connection between the access points so you can connect to our wired Ethernet-based network. And it also does the power over Ethernet feature that gives power to that access point so the electricians didn't have to come up in the ceiling and run an additional electrical outlet to hook up to that point. And then all the wireless access points like people's phones and laptops and tablets and so forth will connect to that Wi-Fi system that's in the closet. So this is a whole nother art and science of its own, is where do we place all these Wi-Fi access points in the network. And in the United States, we have our 11 or 13 channels, and we want to make sure that adjacent devices don't use the same channel. So when it's set up properly, you should be able to roam all over the network and never get disconnected. So what we want to do between ideally these days, between the core layer and the distribution layer, and maybe even between the distribution layer down to the access layer switches, is don't run layer 2 and spanning tree protocol, use some type of routing protocol instead. So OSPF is a great example of a routing protocol that's very scalable. It uses this concept of if you have more than about maybe 50 routers in one location, that's enough in one area. But if you have more offices, more than 50 routers in a location, you can divide that company up or divide the sites, the remote sites of that company up into different OSPF areas. So this is hierarchical based where there's always an area 0, the core area, the backbone area, and OSPF is the area you must start with, must be area 0. And then you can add other areas. You don't have to go 1, 2, 3, 4, 5. So every smart aleck textbook publisher in the world always puts in area 51 just to show how clever they are with these area 51 flying saucer thing in New Mexico. Oh, they're so funny. So you can start with area 0, and everything else must propagate through area 0. If area 1 wants to talk to area 51, all the traffic propagates through area 0. So area 0 is normally going to be at the headquarters of the company. So our area 0 is our downtown Trinity River campus, and all our various other campuses are area 1, area 2, area 3, and so forth. The advantage of distributing these, making all these different areas and having a limited number of routers in each one is, well, OSPF has a mechanism of when there's a change in a topology, he floods the topology change to all the routers just within that area. So if there was a topology change in area 51 or a link went down and everybody had to recalculate their shortest path first tables, it wouldn't bother all the routers in the other areas. Instead, we simply summarize everything in area 51 is summarized back to area 0. Everything in area 1 is summarized back to area 0. We have to manually summarize it, but that's job security for us network technicians and network engineers. So this keeps the change, all the extra flooding traffic isolated to just that areas in which a change has occurred. So this is the only routing protocol now that Cisco is using on their test. Slight exception, you guys that are going to take the CCNA exam, which is supposed to end in February, but they gave everybody a, if you took the CCNA test, you can go and take it until, well, now they're saying July the 31st. I wouldn't be surprised if that stuff gets extended because of the work from home stuff. Big item in the Cisco testing assessment news. You always had to go and report to a Cisco testing center and lock everything up in a locker except your driver's license and go into a room and take the test with all those other infected people. Well, most of those centers are not open now. So Cisco has announced a new thing where you can take a test from anywhere, from your home or from your office. Now, technically, they're going to take some measures to protect against looking up things and so forth during the test. It's kind of similar to what the Tarrant County College is using for our remote courses where you take a test. You have to have a laptop with a camera and a microphone, and there are proctors that watch you when you take the test, and you can't switch to another computer or switch to another tab and look up answers while you're taking the test. So Cisco has set up technology where you're going to run a systems test on your laptop or whatever device you're using. Has to be a webcam so they can see what you're doing. They got to be able to photograph the room you're in. You have to be in the room by yourself. You can't have anybody come in or they'll kick you out of the test. You can't walk out of the room yourself, even to go to the bathroom, or they'll kick you out of the test. You can't have anything to drink except a clear glass of water. You can't have any written notes. They'll give you a scribble board that you can use on the screen. But this is an opportunity now for people that want to take pretty much any Cisco test, except the CCNA. For some reason, they exempted that. If you want to take the new Cisco test or any of the other tests they offer, you can now do this at home or do this from your office. And it's the same exact cost. You just have to go through this system security test first to make sure that your webcam works properly and can see what you're doing, because they're going to be watching you while you take the test. And then you can happen to go out in public and go to a testing center where you'd be closer to 6 feet from other people. Okay, now let's look at some switch hardware. The Cisco 3850 series switches are shown here. And these are kind of like our old 2900 series switches, except they're a newer technology. They use a more modern iOS operating system in them, and they generally support higher speeds. So these could be like access layer switches that can connect to, here we've got some 48-port switches and some 24-port switches that are shown in the diagram. You would put these in the wiring closet to connect to all the endpoints in that building, such as employee desktop PCs and printers and things of that nature. This is the replacement for the older Cisco 3750 switches and 3650 switches that are kind of getting old now, and they're replacing those. Cisco bought Meraki. Now the Meraki series of switches is a lower cost switch for people that don't want the full Cisco line of fully managed, very fast backbone switching fabric switches. Their thing is you have to enable the features on the switch, to configure the switch. You don't configure the switch, you go to a website. It's cloud configured, cloud managed. So you have to pay a cloud fee for your switch to work, and if you stop paying the cloud fee, your switch stops working. I'm not too fond of that myself. I would rather have a switch that I can configure, and since the switch normally has a service life of 10 years or more, I want it to keep working even if I don't decide I want to pay for the Cisco SmartNet maintenance feature. Or maybe our department ran out of money, we couldn't get it. Now, if you're a service provider, like an internet service provider or a hosted web provider or something of that nature, there are some very large switches that provide, and these are $1 million in the price class of around $1 million switches. They have a lot of features in them. They can have like 300 or 400 ports in them, for all your connections. Now, these are normally not going to connect to user endpoints. You're going to use cheaper access layer switches for that. Instead, you're going to use these switches as the backbone, the core layer or the distribution layer of your company if you're a service provider. The bottom series is some switches that kind of look like a home router on steroids. It's got a 4-port Ethernet switch. It's got 2 gigabit Ethernet ports to go to a connection to the leased line connection to go back to the rest of the world. It's got, if you look to the left part, it's kind of hard to see there, it's got 2 power supplies. It's got 2 plugs to plug in. So that way we have some redundancy. We can plug one power supply into one circuit breaker and plug another power supply into another circuit breaker, and at least have the ability of the switch to continue operating even if one of the power supplies fails. Or make one on the UPS and one on the commercial power. So in form factors, we have our cheaper access layer switches. They're fixed. They only have what they came with. Then we have our stackable switches that look like fixed configuration switches, but you can stack 8 or 9 of them together and make them act as one switch with one management address. And then we have our modular layer switches that you can plug in extra cards and add ability, scalability in the field. We can add something to them to add more ports as we need them. So this is the back of Cisco 8 or 9 switches that are stacked together. Normally, in our lab, we'd have to put an Ethernet cable between the 2 switches to stack them together. Like most of the labs, you put port 01 from one switch to port 01 to the other switch, and you do trunking between them. But that costs you some ports on your front panels. So in the stackable series of switches, we get all of our front panel ports are available for our printers and desktop employee PCs and telephones. And we have special dedicated wires on the back of the switches that tie them together and make them one single unit, one IP address. You can manage all the switches from one IP address. He talks about rack mount units. A rack mount unit is a 1 3/4 inches or 1 U unit. So the switches that we have in the lab are 1 rack mount space. The routers that we have in our lab in 1941, those are 2 rack mount spaces. So the port density is how many ports are available in the switch. So the access layer switches that are on the left, some of them have 48 ports and usually a couple of gigabit or 10 gigabit uplink ports as well. Some of them would have a more limited number. So the ones we have in the lab only have 24 fast Ethernet ports and 2 gigabit uplink ports. The ones in our wiring closet have 48 gigabit Ethernet ports to go out to the classroom computers, and then a couple of fiber optic connections that link the switches together to all the other switches in our campus. Modular switches can have, this is the number I keep seeing, 384 switch ports in them. Some of them could be fiber, some of them could be copper. So this particular switch on the right has been configured with like 7 48 port blades that are plugged in. And so you can get as many switches as you can get. You can get these chassis in larger or smaller sizes. The one we have in the back of the classroom only has about 6 cards that can be plugged in, but you can get ones that are as big as a deep freeze or a very large refrigerator, and they have room for lots of card slots in them. So if you go buy a switch from, say, Fry's Electronics or Office Depot, it doesn't have what I call the switching fabric, the forwarding rate. So you say you buy an 8-port switch from Fry's and it's gigabit Ethernet ports, and you plug in 8 servers and you run this program. There's a program called iPerf that'll generate endless traffic. And so all 8 PCs that you build in your A+ class are sending out 1 gigabits of data continuously and receiving 1 gigabits of data continuously, all 8 ports at the same time. And that's a grand total of 16 gigabits of data. And that little $30 switch from Fry's doesn't have the silicon. He doesn't have the switching capability to do that. They're going to be slower than that. So the forwarding rates are going to be slower. Now, if you get a Cisco switch and you plug in 24 Ethernet, gigabit Ethernet devices to it, it's going to have the electronics in it to do the full speed gigabit up and a gigabit down simultaneously on all 24 ports. But it's going to cost you a lot more than $30. It's going to be more in the $1,000 range for gigabit Ethernet ports. So the problem is if we use cheap switches, then we might have latency and things might slow down. In a small business operation, it probably wouldn't matter too much. But in an industrial environment, a large corporate environment, this is why we typically use managed switches, and they cost a lot more. So in the case of Tarrant County College, we just go to the taxpayers and get bond money, and we can buy new stuff whenever we want to. Okay, the power over Ethernet feature is the one that if we have a device that we don't want to, if it's inconvenient or expensive, we don't want to have the electricians come in and run a 120 volt duplex receptacle outlet there and wire it back to a fuse box or load center somewhere. Typically, devices that need this power are Cisco or IP telephone sets, Wi-Fi access points, surveillance cameras, IP surveillance cameras in a warehouse. We're going to have to run the Ethernet cable to it. So can we just have that Ethernet cable provide double duty? Have it both provide the Ethernet connection for the data from the IP surveillance camera up in the top of the 40-foot warehouse, and also provide the power for that device. So this adds some cost to an Ethernet switch. The Ethernet switches we have in our lab do not have power over Ethernet in them. It adds a minor cost. It's not a great cost. It doesn't double the cost of the switch. It only adds 10 or 15% to the cost of the switch. And there are different levels of power over Ethernet required by different devices. Some of them require about as much power as a Christmas tree bulb. Like a voice over IP telephone or Wi-Fi access point, they only need 5 or 10 watts. But some other devices require great amounts of power. So there are varying amounts of power over Ethernet standards that go up to 60 and 90 watts. This is hard to believe, but Cisco is actually marketing lighting fixtures that run over power over Ethernet, so that when people leave the room, the technology can turn off the switch automatically. And there are modern lighting fixtures that are LED that can light up as bright as the old fluorescent fixtures did that required 200 or 300 watts on 60 or 90 watts. Now, multi-layer switching. Oh yeah, I talked about the marketing guys went to Hawaii, drank a bunch of rum, and came up with a bunch of new terms. It was perfectly clear to me that a layer 2 bridge was a data link layer device they received and forwarded Ethernet frames. And then they came up with the name switch because they didn't like the name bridge. And it was very clear to me that a router was a layer 3 device that forwarded IP packets based upon their layer 3 IP destination network address. So the technology started getting real good, particularly about 20 years ago. And they started building some features in what we don't call them multi-port bridges anymore, we call them switches. A switch is a device that replaced the old hubs. Looks just the same, has 24 ports on it, but it has much better performance. So the multi-layer switches were probably not deployed at the access layer. We're going to use a cheap $500 Cisco switch for that. But the core and distribution layers, they're going to do multi-layer stuff. We're going to do maybe routing protocols between them. We're going to do access control lists. So we need to have a blade in that modular box that's essentially a router on a blade. And we can plug in and do everything we could do with a router. So these more expensive $40,000, $1 million core and distribution layer switches have very fast processing power. Think of it as a comparison between a desktop level employee PC that costs $500 and a server that's in a rack mount closet that costs $20,000. The server has much higher performance than the desktop PC does. And it's expected to last 5 or 10 years. Whereas the desktop employee PC, it's out of date within 6 months. And if it breaks, we'll just go to Fry's and buy another one. So in multi-layer switching fabrics, they can actually forward IP packets about as fast as switches would normally forward layer 2 data link layer frames. And they use very specific, very fast silicon hardware, application specific integrated circuits. So what they do is they break the all this redundancy in a router is all the software's got to go through the routing table and look through, well, if it's a service provider, 750,000 entries. Well, we have our parent routes and we have our child routes and things of that nature. We try to do to speed it up. But the very fastest thing we can do is distill that routing table down to a forwarding information database and put it in a piece of silicon and get super fast performance of all the packets that are going through that routing device that's in that multi-layer switch. So this is what you're paying the big money for in these big devices. So when we're looking for in a business, we need to choose a switch. Well, cost is always going to be a big consideration. And if you're fortunate enough to work for a company that the chief information officer, the chief technology officer is a peer with the chief financial officer and everybody else with the chief executive operating officer, you're in good shape because you're going to be able to talk to them in business terms and make a case how this is a technology value center. We're going to bring value to the company and increase the profits of the company if we can get some high quality equipment here. If you're unfortunate enough to work for a company where you, the IT guys report to the chief financial officer, well, you're going to be a tough sledding here to approve this new equipment because chief financial officers are trained to regard everything as an expense to be reduced, and you're going to have a hard time getting this equipment for this stuff. But at any rate, it's going to come down to the cost of the switch. If you want power over Ethernet, it's going to be more expensive. If you want 48 ports instead of 24 ports, it's going to be more expensive. We talked about port density. Is it going to be 24 ports or 48 ports? So in our wine closet, we have very limited space. It's a very small closet. So we have to use 48 ports to get the maximum number of ports in there and not overflow that small rack that's in that wiring closet. For power, power over Ethernet, for things like IP telephones, IP surveillance cameras, Wi-Fi access points, and even some compact switches that you might put in a remote area like a classroom, they can be powered over Ethernet as well. There was another feature called power over Ethernet pass-through where it can go to the additional switches. We want reliability. We want that triangle-shaped configuration that connects together the access layer to the distribution layer to the core layer, so that if any one wire gets chopped up or any one switch loses power, there's minimal disruption in the company operations. Port speed, well, our poor little $500 switches only have fast Ethernet to most ports. They only have gigabit Ethernet on the uplink ports. So in the modern world today, you probably would want to go with gigabit Ethernet to your employees' desktop PCs and 10 or 25 or 40 or 100 gigabit uplinks to the rest of the network. Modern high industrial quality managed switches have frame buffers in them enough where if there's congestion, the buffers will store all the data without losing data. So for example, if you're sending the data up to the switch at 1 gigabit of data, and then he's sending it to the server at 10 gigabits of data, that's storing forward. You can't do fast switching with this because you got to store it in the frame buffer and then shoot it out at the higher speed. And when the 10 gigabit server sends the answer back to you, it's got to be stored in the buffer and then dribbled out to you at your slow gigabit Ethernet speed that you've got. Okay, scalability, fixed configuration switches, no scalability, buy another switch. Stackable switches, yeah, buy another switch, but plug it together on the back and don't lose any ports on the front, slight additional expense. Modular switches, just plug in a new board into an empty slot. Maximum expense, but highest performance. So hopefully you're working for a company where the IT head honcho is a peer with the chief financial officer and the chief information security officer, and they all will present their case to the chief operating officer, chief executive officer. Okay, now let's look at some router hardware. So routers are layer 3. Traditionally, routers are layer 3 devices that use the network address, and they look through the routing table, and they look through the routing table to find which interface port should I use as the exit interface to send this to. If we're doing load balancing, if we can use RIP, what I forgot to mention earlier, if you take the CCNA test, there's no OSPF on the CCNA test. He wants you to understand RIP. So on the routing and switching essentials class, the second Cisco class here, we had a little bit of a RIP protocol. There will be no EIGRP, there will be no OSPF. Maybe at a high conceptual level, you might have to understand that OSPF is a link state routing protocol and EIGRP and RIP are distance vector routing protocols, but no configuration questions of any kind. But in the future, it's only OSPF only. It's going to be the only routing protocol in the CCNA objectives. So every routing protocol, doesn't matter whether it's RIP or EIGRP or OSPF, they all support load balancing. And no spanning tree protocol required at layer 3. They simply round robin the packets, packet 1 to the first link, packet 2 to the second link. And if one of those links goes down, they'll simply use the remaining link to, it'll be slower, but you'll still be connected. And all host machines, like employee desktop PCs on the network, they're going to specify as that default gateway value, that Ethernet interface that's most closely connected to them through some 24 or 48 port switch. So routers filter broadcast. A broadcast that comes into one port of a router doesn't go to out the other port of a router to anything else. Broadcasts, now switches on the other hand, are compelled to flood broadcasts on all the other ports. So we want to keep the number of people in a single broadcast domain to a reasonable level. And when I say reasonable level, somewhere between 50 and 200 is tops. You don't want any more people than that in a single broadcast domain. So that's one reason why anytime you go out and look at any network installation today, pretty much always it's going to be a /24 or 255.255.255.0 subnet mask, which is 8 host bits, well, 2 to the power 8 minus 2 for the network address, the broadcast address, 254 available addresses. You don't want to exceed that. You don't want to make it a 23 or a 22 or a 21 and have 1,000 devices in one broadcast domain. So routers limit the broadcast. They don't send the broadcast out to other areas. No one's interested in your ARP request to find your printer over in the other building across campus. Routers connect geographically separated locations. We hire a private WAN link, or maybe we'll use an internet connection and virtual private network technology to connect our various branch offices together. Problem with using the internet for this is there's no quality of service. So our phones might sound terrible. You want a private WAN link to do something like that. We can normally group users by typically a department within a company, so that the advertising department can be in their own broadcast domain, and the marketing department's secret marketing plan for next year, they don't have to worry about other people trying to do some sort of way of breaking in and learning that secret broadcast, learning that secret marketing plan that then no one is supposed to see until it's released to the public. And routers can do security because they have access control lists. So for example, in a public school environment, we might not allow the kids under 13 to access the internet, and the kids over 13 might have some limited access to the internet. So here's some 1U, 1 3/4 inch rack mount, smaller Cisco access routers. These are optimized for use at a branch office, a small office that's part of a larger company. Integrated service router ISR line came out about 15 years ago with the Cisco 1841 routers. That's the batch we had before we got our newer batch. They were integrated service router 1. The current routers we have in the lab are integrated service router 2, the 1941 routers. And now the replacement model for this is the 4000 series routers. These are actually running Unix and Linux as the operating system, and it looks like iOS to you. So that does the same sort of thing any branch office router would do. It has Ethernet connections to go to your Ethernet switches at that branch office. And then the older routers might have a serial port that went through a T1 line or something. But these days, we're not seeing so much serial port anymore. We're normally seeing multi-protocol label service or Metropolitan Ethernet or some other technology that's an Ethernet handoff technology. So you just plug a box that the vendor gives you into the Ethernet port of your router. The types of routers that service providers and big corporations would use look more like these big switches that we saw earlier. These are $50,000 on up to $1 million routers that would handle. We need our little branch office routers, our 1941 routers. You can't put 750,000 routes of a border gateway protocol table in the routing table. They don't have the guts for it. It would be like trying to use a cheap $500 Dell desktop computer as the Microsoft Active Directory Domain Services primary domain controller for the entire company. It wouldn't be able to handle it. So with routers, similarly, we need a high-powered router that has 750,000 route capability in it. We have thousands of customers connected to this. We need high performance. So when you pay an internet service provider, you're essentially leasing a little bit of capability on that high-performance router. Just like I'm leasing a little bit of capability at the service provider, the web hosting provider that's giving me 1% of its CPU cycles for my Cisco24.com website. So service provider routers, look, this one is huge, just like the size of a big refrigerator. 6,000 series routers. So lots of connections, lots of processing power. Now, this Cisco does make some ruggedized routers for use in harsh industrial environments. So Example on the right here, we've got a router that might go in an industrial environment where we've got 4 Ethernet ports and a couple of uplink ports to go back to a service provider's Ethernet handoff technology. These are more expensive than regular switches and routers, but they're built to run in a rugged environment like a dirty power plant with lots of oil and grease around it. So see, this one kind of looks like a small branch office. It looks like a home router. It's got the 4 Ethernet ports for the few devices at that branch office, and it's got some uplink ports to attach to the connection we have to go back to the home office. A little bit more expensive than a Linksys router, which is about $20 to $40. And then for service providers, this is the same photo we had before. We have all these routers that are very scalable. You can add cards and add features, get hundreds of ports in them, and this has the high capability features like the ability to have hundreds of thousands of routes in your routing table. The newer series 5500 routers, you might put these in a large data center, like something that Google would use, or something that a company that had their own data center, where have you heard this term, continuity of business operations? If there's a disaster of some sort, and our one data center there's an earthquake and it loses power, there's a fire, we want to be able to instantly transfer stuff to another backup data center that we can continue our operations on. So Tarrant County College has got what's called a cold data center in Irving. If something were to happen to our data center in downtown Fort Worth, within a matter of an hour or two, we could bring up all our business operations at our backup data center in Irving. We have to do some backup and restore, but that can be done very quickly. Other companies have what are called hot data centers, duplicate data centers in different parts of the country, where if one data center in one part of the country gets hit, operation is seamless. It just simply continues all the time. When we talk about the VMware virtual machines, VMware has a feature called VMware in Motion, where you can instantly migrate a server from one machine that's failing to another machine that's a backup machine, and the users, they never even time out. They continue seeing stuff. Okay, and here's this same industrial version of that router we saw earlier. It's designed to run off in industrial power plants. They have 24 and 48 volt DC power buses. They can run off that instead of 120 volt AC power supply. And it's a ruggedized remote router that would have 4 Ethernet ports and then uplink connections to the rest of the world. Okay, I think I've covered it for today. No lab assignment for this, so you guys enjoy your weekend off. We'll see you again Monday, and we'll pick it up again with Chapter 12 and onward. So nice to be with you guys today, and I look forward to meeting with you guys again next time.